Yeah, good morning all the students. Did you try in this calculation of entropy and information gain, what have been taught in the last class? Did everyone try how to calculate them? Okay, let us go from beginning once again so that it will be easy for you to understand. As this is a compulsory question you get in your exams, let us do it from the beginning once again. Okay, in the last few sessions in this chapter, we have gone through this basic decision tree algorithm and which attributes would suit as a best classifier. Right? And that we are going to learn with an illustrative example. Now we have practiced how to calculate the measures of entropy and information gain, right? Now, from the knowledge you have gained in your last session, can you tell me whether entropy is directly related to information gain or inversely related? I want you to answer, students. If you sit silently, I can't understand whether you understood or not. In entropy and information gain, they are inversely proportional or directly proportional. I mean to ask, if in entropy increases, information gain increases or it decreases? Any one of you? What is the relationship between entropy and information gain? Yes, tell me. When entropy increases, what will happen to information gain? What will happen to information gain?
Decreases, ma'am.
It decreases, very good. And when entropy reduces, information gain increases. So what is the objective of this ID3 algorithm? It is to reduce the entropy so as to achieve more information gain. So you need to calculate the entropy for each of these attributes. Now, whenever the entropy is less for an attribute, it tells that information gain is more with that particular attribute. When that gain is more, it can better classify the training examples, right? That is how we need to understand about these two measures, entropy and information gain, right? Now let us once again see how to calculate this entropy and information gain as we proceed with this example, right? Now we have taken this training example set having total 14 days data based on climatic conditions measured with respect to these parameters: outlook, temperature, humidity, and wind. And what is the target variable? That is the outcome variable. Play tennis, whether tennis is played on that day or not, given the climatic conditions on those days. Now the machine has to learn from these 14 training examples and it has to generalize with an unseen example. Generalize well with an unseen example means if a new day's data is given with respect to outlook, temperature, humidity, and wind, it has to predict whether tennis can be played on that day or not based on its experience it has derived from the training examples given during the training process. Okay, that is how this problem has to be understood. Now, for this machine, we are asking it to follow ID3 algorithm, right? Means the machine has to construct a decision tree and make a good fit with that decision tree to the training examples, right? That is the problem at hand. Now there are total 14 training examples described by attributes including wind, outlook, humidity, all those, right? Now let us take wind attribute, okay, which can have the values weak and strong. Let's go back to the training example. See, under wind, what are the values, possible values under wind column? Under this column, what are the values you have for wind? Weak and strong, right? These are the two values. Now, of these 14 examples, suppose 6 of the positive and 2 of the negative examples have wind equal to weak. So we can write that like this, S of weak. The training examples with wind value as weak are 6 positive examples and 2 negative examples. Total, how many positive examples are there in the training examples? 9 positive examples and 5 negative examples. Okay, means 9 examples having outcome label as S and 5 examples having outcome label as no. Okay, now in that we are taking training examples where the wind value is weak. How many of them are there here? 6 positive examples and 2 negative examples. Right? In the same way, let us take the training examples where the wind value is strong. How many of them are there? Reminder, say 6, 7, 8, right? So 6 more examples are left out. So 3 positive examples and 3 negative examples have wind value as strong, right? Now you have to calculate the entropy for this wind attribute for all the possible values. First you have to calculate for S weak and S strong, then give that entropy in the information gain so that it will calculate the information gain for the attribute wind. What I'm telling is, first you have to calculate the entropy for S of weak, then calculate the entropy for S of strong. How do you calculate entropy for S of weak? See this, there are 6 positive examples and 2 negative examples. What is the formula? Sigma Pi minus Pi log Pi, right? That is the formula for entropy. So when you want to calculate the entropy for S of weak, how do you calculate that? Minus 6 by 8 log 6 by 8 minus 2 by 8 log 2 by 8. That will give you the entropy for S of weak. Then in the same way you calculate the entropy for S of strong also. Now substitute that in the information gain. What is the formula for information gain? Ig. It is the entropy of the total training examples minus the number of training examples with wind value as weak by the total number of training examples with the entropy measured at training examples having weak as the value minus number of training examples having wind value as strong divided by the total number of training examples multiplied by entropy of the training examples when the wind value is taken as strong. That's all. That is the formula. Calculate each attribute's entropy for each of the values. Put that in the information gain. You will get the information gain for that attribute wind. For wind. Okay. Anyway, this calculation we'll be seeing in the slides coming up so that you'll understand more better. Okay. Now see, the information gain due to sorting the original 14 examples by the attribute wind may then be calculated as, how to calculate this? First of all, what are the possible category, possible attribute values for wind? Weak and strong, right? That we know very clearly. Now, how many training examples are there totally? 14. Out of them, how many are having positive label? 9 plus 9. And how many are having negative labels? 5. Right? There are 14 training examples. Out of those training examples, 9 are having positive label and 5 are having negative label. Okay, till here it is clear. Now, take the training examples where the wind value is weak, because you are calculating the information gain for wind. You're calculating the information gain for wind. You have to calculate the entropy for each of the possible values of wind, right? So what is the entropy for S weak? How to calculate that? First, you have to see how many number of training examples are positive and how many of them are negative, which are having wind value as weak. Okay, that you can count from the training example set. It is 6 and 2. Now, go for the wind value as strong. How many of the training examples are positive, having wind value as strong? 3. And how many of them are negative? 3. I'll show you how to count this. Let us go back. Now, under the wind attribute, you just see strong 1, 2, 3, 4, 5, 6. Total 6 training examples are having wind value as strong. Out of them, how many are having no label? 1, 2, and 3. How many of them are having S label? 1, 2, and 3. Right? That is how you need to calculate, how you need to count. Now see this, number of training examples having wind value of weak is 6 positive and 2 negative. Number of training examples having wind value as strong is 3 positive examples and 3 negative examples. Now, how to calculate the information gain for the wind attribute? How does the ID3 algorithm proceed? It will calculate, in the first step, it will calculate the information gain for all the attributes, outlook, humidity, wind, like that. Now, wherever the information gain is high, that will be placed at the root node of the decision tree, because it gives more information gain, because it reduces the uncertainty in the classification. Got it? That is why the information gain should be more for the attribute selected at the root node. Now let us see how information gain is calculated. First, we are calculating the information gain for wind attribute, right? How do you calculate the information gain? The entropy of total number of examples. Total number of examples are 9 positive examples and 5 negative examples. How do you calculate the entropy? Minus 9 by 14 log 9 by 14 minus 5 by 14 log 5 by 14. This will give you entropy of the entire set of training examples. Got it? Now, what is your next step? From that entire set of training examples entropy, you have to remove entropy of the attribute wind. But wind has 2 values. So you have to calculate the entropy with weak and entropy with strong values, right? That is what we are doing. Minus, see here, the operator here, minus, add up entropies of the values, training examples having wind value as weak, plus wind value as strong. Both have to be subtracted from the total entropy of the training examples. So how do you do that? Entropy of S minus, see here. You have to calculate the entropy for weak minus the entropy for strong, right? Now you see here carefully what is the second term. Entropy of weak, when you're calculating the entropy of weak, it should be multiplied by the training examples having entropy as weak by total number of training examples. So how many training examples have entropy and wind value as weak? 6 plus 2. Total 8. 8 by total number of training examples in the training set given 14. Now entropy of S of weak. How do you calculate entropy for this? S of weak? It is simply minus 6 by 8 log 6 by 8. How did you get this? Proportion of positive examples in the total examples. What is the proportion of positive examples? 6 by total examples 6 plus 2, 8. So it is minus 6 by 8 log 6 by 8 minus, what are the proportion of negative examples? 2. So it is minus 2 by 8 log 2 by 8. That will give you this entropy where the wind value is weak. In the same way, calculate entropy for wind value as strong, right? So how many of them you have here? See this part. Number of training examples where the wind value is strong. Total examples are 6. That is why you are writing 6 here, divided by the total number of training examples, multiplied by entropy strong, right? So how you are doing this entropy of strong? You give the value as minus 3 by 6 log 3 by 6 minus 3 by 6 log 3 by 6. That will result as 1. Entropy of strong as 1. Okay, that you substitute. Always remember, when you're calculating in your scientific calculators, you have to take this log as base 2, not as base 10. Okay, it is base 2. And one more suggestion I'm giving you is, whenever you're calculating log of 6 by 8, convert 6 by 8 into a decimal number. Decimal number. So 6 by 8, it will give you around 0.8 something. 0.60, right? 0.7. Okay. Now calculate log of 0.7. Do not calculate directly log of 6 by 8. Okay. Now when you calculate this entire thing, you will get as 1. When you calculate this entire thing, you will get as 0.811. Now substitute that in the formula. You'll get the information gain for the attribute wind as 0.048. Means what the algorithm is trying to obtain here is how much better classification, it can make by using this particular attribute wind. It will get an information gain of 0.048, right? Like that, it will calculate the information gain for outlook, it will calculate the information gain for humidity, and it will calculate the information gain for the other given attribute. Now, wherever the information gain is more, that will be the root node of the decision tree. Okay, so information gain is precisely the measure used by ID3 to select the best attribute at each step in growing the tree. Okay, now wind is taken, say wind has more information gain, that is taken as the root node. Now wind, slow, strong, or normal, strong, it will come here. Now calculate the information gain for remaining attributes, do not include wind. So among the other 3 attributes for which attribute the information gain is high, that will be taken as the condition here. Again, you proceed with that you proceed with the labels of that particular attribute. Again, if it is able to classify properly, that will be the leaf node. If it is not still able to classify purely, in that case, it has to proceed with another condition, right? This is how the decision tree is built iteratively by ID3 algorithm. Okay, now let us take the same example and see further how the tree is constructed. Now in this case, you see in this figure, the information gain of 2 different attributes, humidity and wind is computed in order to determine which is the better attribute for classifying the training examples. See, it is very clearly represented in this figure. Total number of training examples you have 9 and 5, total 14. Of them, 9 are positive and 5 are negative. Now, how is the entropy calculated for this? You know the formula. Minus 9 by 14 log 9 by 14 minus 5 by 14 log 5 by 14. That will give you the entropy for the entire training example set. Now, humidity has two values in the training set, high and low. So whenever it is high and whenever it is low, you have to calculate the entropy. Now, whenever the humidity is high, there are 3 positive examples and 4 negative examples. Out of 7 examples having humidity as high. Now, what is the entropy that is calculated? It is easy for you to calculate, right? Now, if you have 3 positive examples and 4 negative examples here, how do you calculate the entropy? Minus 3 by 7 log 3 by 7 minus 4 by 7 log 4 by 7. That will give you 0.985, right? Now you come to the other branch. If the humidity is normal, in that case, out of 14 examples, out of 14 training examples, 7 training examples are having humidity as normal. Out of them, 6 are positive examples and 1 is negative example. Why you are taking the proportion of positive and negative examples? That is required by the entropy formula. Now again you calculate the entropy here. How do you calculate that? Minus 6 by 7 log 6 by 7 minus 1 by 7 log 1 by 7. That will give you the entropy 0.592. Got it? Now, how to calculate the information gain for humidity? Gain S, humidity means gain from these training examples. Information gained by the decision tree from this set of training examples S with respect to humidity. This is how you need to understand. I'm repeating how you read this. Information gain that is achieved from these training examples, set of training examples S, by using humidity as the attribute for classification. How much is the information gain? Substitute the entropies in the formula. Total entropy 0.940 minus number of training examples having humidity value as high 7 by total number of training examples 14 multiplied by entropy of humidity high, that is this value 0.985, that is substituted here, minus total number of training examples having humidity as normal, that is 6 plus 1, total 7 out of 14 training examples multiplied by what is the entropy where the humidity value is normal? 0.592. So what is the result you get? What is the information gain you get here? 0.151. Got it? Now come to the other part, this part. Now let us also calculate what is the information gain for wind attribute, so that we can make a choice between humidity and wind, which should be the root node for the decision tree or a root node for the subtree in the decision tree. Not only a root node, whenever a subtree, whenever a tree has to be built or a subtree has to be built, it should have a root node, right? And that root node should contain some condition. Now that condition should be applied on an attribute. Now how that attribute is selected? Based on the information gain. So at each root node, this IT3 algorithm will calculate the information gain of the remaining attributes which are not covered in its ancestor root node. That information gain is considered, which wherever the information gain is high, that will be selected as the classifying attribute. Okay, now you're taking this wind here. Now when the wind value is weak, how many training examples have wind value as weak? 8 training examples. How many of them are positive, students? How many of them are positive? 8 training examples have wind value as weak. How many of them are positive? I am indicating it here and it is clearly seen on the picture. Still you are not able to answer? How many of them are positive examples?
6, ma'am.
How many of them are negative examples?
2.
Right. Now how the entropy has to be calculated? Can any one of you give the formula? How the entropy is calculated? Proportion of training example, positive training examples and proportion of negative training examples minus proportion of positive training examples here is 6 by 8 log 6 by 8. Proportion of negative training examples 2. 2 by out of 8 training examples log 2 by 8. This will give you the entropy 0.811, right? Now again, take the other branch. What is the entropy when the wind value is strong? Total how many training examples have wind value as strong? 6 training examples. Out of them, how many are positive? 3. How many are negative? 3. When there are equal number of positive and negative training examples, you have entropy as 1. You know that from the explanation given to you about the entropy. When you have all positive training examples and no negative examples, the entropy is 0. But when you have equal number of positive and negative training examples, the entropy value is 1. Got it? Now here the entropy value is 1 because there are equal number of positive and negative training examples. Means because of using this particular attribute, you are not able to make pure classification, means you're not able to learn better from the training examples given, right? So what is the information gain for this wind attribute? Again, substitute them. Entropy of total training examples minus entropy when the wind value is weak minus entropy when the wind value is strong. Each of them multiplied by the number of training examples for that particular value. So that will give you 0.048. Now among these two attributes, humidity and wind, which is having higher information gain? Students, which one is having higher information gain? Humidity or wind? Which one is having higher information gain? Speak out. Nearly 40 people are there in the class and none of you are able to answer this. This is the second time I'm repeating this example and you're not able to answer. Or do you think it's a silly question to be answered? It is beyond, very below, very lowest question given to you according to your intelligence. Tell me which attribute is having highest information gain in these two cases.
Humidity, ma'am.
Yes, humidity is having highest information gain. So that can be selected as the attribute for that particular node, root node, whether it is for the main tree or whether it is for a subtree. Okay. Now let us still see how this tree is iteratively built further. Okay. Now humidity provides greater information gain than wind. That is what you have answered. Relative to the target classification. Yes or no. Now here E stands for entropy and S for the original collection of examples. So you are very comfortable with the terminology, right? E is the entropy, for S the original collection of examples. Now given an initial collection S of 9 positive and 5 negative examples out of total 14 examples, Sorting these by their humidity produces how many collection of examples now? 7. Out of them, 3 are positive and 4 are negative, having humidity value as high. And 6 of them are positive and 1 is negative, having humidity value as normal. Now the information gained by this partitioning is 0.151 compared to the information gain with wind is only 0.048. So which is the best classifier attribute? Which attribute is the best classifier? Humidity. That is how you need to understand. Now let us see from beginning. We have just seen an example between two attributes how the information gain can be compared. Now let us see from beginning how a decision tree is constructed by ID3 algorithm for this particular training example set given. Okay, consider the first step through the algorithm in which the topmost node of the decision tree is created. How the topmost node is created? By calculating the information gain of all the 4 attributes. Right? Now ID3 determines the information gain for each candidate attribute. What are the attributes? Outlook. Information gain for outlook is calculated. Information gain for temperature is calculated. Information gain for humidity is calculated, and information gain for wind is calculated. Then selects the one with highest information gain. Right? So for your quick understanding, the information gain is given here, but when you are working out a problem, you have to calculate the information gain and list them like this so that it will be easy for you to select which one has to be used as the root node. Now tell me, among this outlook, humidity, wind and temperature, which is having the highest information gain?
Outlook.
Very good. Outlook is having highest information gain. So outlook will be taken as the root node. Got it? Now, what are the outlook values? Sunny, overcast means covered with clouds, sky is covered with clouds, and rainy, right? These 3 are the values. Now, when the outlook is sunny, what should be the next split point? Or whether it has already completed the classification, that we have to check. Okay, now let us go back once. See here, outlook where it is overcast and outlook when it is sunny. How many of them are positive examples and how many of them are negative examples? That we have to see. So there are total 1, 2, 3, 4 and 5 values as sunny. Out of them, how many are positive examples? 2 of them are
2 are positive.
very good. 2 of them are positive examples and 3 are negative examples.
Negative.
Yes, correct. So we can write here 2 are positive and 3 are negative. Is it a perfect classification it has provided? Either all of them should be positive or all of them should be negative. That kind of classification has to be made. But still there is uncertainty in the classification by using outlook sunny. Okay, so keep it now. Now come to overcast. For overcast, the outcome label is S. For second overcast, it is S. Third and fourth also it is S. Means out of 4 positive labels, out of 4 training examples having outlook value as overcast, all are positive, no negative examples. Got it? So there is a perfect classification here. The entropy value will be 0 here. Right? So this can be your leaf node giving overcast when the outlook is overcast Tennis is played or not? Yes, it is played because there is perfect classification. There is very pure classification being done by taking this outlook value overcast, right? But with sunny, still no pure classification is done. You have 2 positive and 3 negative examples. With rainy, you may have 3 positive and 3 negative examples. Is that classification pure? No. If the classification is not pure, it indicates that your tree has to be extended. Now, how the tree should be extended? Again, information gain of remaining attributes have to be calculated. Now, when the outlook is sunny, you have 3 possible options. When the outlook is sunny, what is the temperature value? What is the humidity value? And what is the wind value? Right? So that has to be calculated. Now for this, you have to take as S of sunny. You have to calculate the information gain for temperature. S of sunny, you have to calculate the information gain for humidity. And S of sunny, you have to calculate the information gain for wind. Right? Why you're not taking outlook? Outlook is already covered in the root node. So it has to be removed. That is your step given in ID3 algorithm. Do you remember? Whatever attribute considered in the root node, that has to be eliminated for the next information gain calculation. Okay. So when the sky is sunny, what is the temperature? How many of the positive examples and negative examples you have? When the sky is sunny, what is the humidity? How many of the positive and negative examples you have? When the sky is sunny, what is the wind speed? How many of them are positive and negative examples you have? Right? Now, you have the values. You calculate the entropy. Entropy for this combination, and this combination. When you have the entropy, you can calculate the information gain. Calculate the information gain for temperature, calculate the information gain for humidity, and calculate the information gain for wind. Say, humidity has the highest information gain. That should be the attribute which should be taken as the classifier for this branch. Now, when the humidity is normal, what is the classification given? When the humidity is high, what is the classification given? When these two classifications are giving pure classification, means most of them or all of them are training examples, are positive training examples, or all of them are negative training examples. That is the end of your particular subtree. If at all there is still no pure classification, like in this case, if there is a pure classification, you stopped it. But because there is no pure classification here, you extended. Now after this also, if you don't get pure classification, you have to extend the tree further. But if you get a pure classification, that will be your root node. Yes or no. Got it? In the same way, calculate for outlook rainy, how many of them have, wind, this is not rainy. 1 second. Yeah, this is rainy. Here, in this case, calculate again for humidity is already used. Calculate for temperature and wind. Because for humidity, you have calculated that information gain is high and you have already used that attribute in the leaf node. Now, what are the remaining attributes for which entropy has to be calculated? Only wind and temperature. Wind and temperature. These two are remaining. Now, calculate the information gain at this point for temperature and wind. Now, it is found that wind is having higher information gain. So, wind is taken here for further classification. And it is found that it is giving pure classification. So you can stop your decision tree there. Did you notice one thing? In the root node, outlook is used. In the subtree nodes, humidity and wind is used. but nowhere temperature is used because temperature attribute is not giving high information gain. That you can notice here, see. Temperature has many values, hot, mild, cool, right? And it is having equal number of training examples, means all of them are prevalent. Temperature is having more number of training examples with hot, more number of training examples with mild, more number of training examples with cool. So that can't be taken as a attribute for classification. It doesn't give better classification because information gain with that temperature attribute is very low. That is not at all considered in the decision tree algorithm. Got it? That is how a decision tree is built iteratively by the ID3 algorithm. At each step, it calculates the information gain for each of the attributes, and wherever the information gain is high, that attribute is taken as the root node. Now, leaving that attribute, remaining attributes information gain is again calculated at the next step, and wherever the information gain is more, that attribute is taken as the classifying attribute. Split point. That, see here, outlook is called as the split point. Here humidity is called as the split point. Here wind is called as the split point. Okay, so it calculates that it find out that split point based on the information gained by the attributes, right? Now you can see very clearly. Now you have clear explanation about how a decision tree is built. Now see, that is figuratively represented here. Initially, understand this once again very clearly. Initially, there are 14 training examples. Out of them, 9 are positive and 5 are negative. Say, if at all 14 are positive and 0 are negative, what will happen in ID3 algorithm? First step, you need not construct any decision tree. Why? Because all the training examples are already classified. You can't learn anything better from the training examples. Or say if you have 0 positive examples and 14 negative examples, that is your second step in ID3 algorithm. Means all the examples belong to the negative class. Then there is no use in learning a classification from that. You can't learn anything from that, because all possible training examples given are negative examples only, right? So when does the problem start? When you have a good proportion of positive examples and negative examples, then your problem starts. Now, after calculating the information gain with outlook, humidity, temperature and wind, ID3 algorithm found that outlook is having more information gain and is providing better classification, right? So that is taken as the root node. Got it? That is why outlook is taken here. Now outlook has how many values? 3 values: sunny, overcast and rainy, right? Now when sunny is taken, how many of the training examples are having outlook value as sunny? D1, D2, D8, D9, D11. Total 5 training examples are having outlook as sunny. Out of them, is the classification pure? No. 2 of them are still positive and 3 of them are negative. No pure classification is made. Now leave it here. Come to the overcast branch, this middle branch. Now, how many of them are classified as positive and how many of them are negative? D3, D7, D12, D13. Total 4 training examples are having outlook value as overcast. Out of them, all 4 are positive examples. There are no negative examples. Means outlook, whenever the value is overcast, on all the days tennis is played, there is a perfect classification given there. There is no doubt about the other attributes. It doesn't care about the other attributes. That is why you can give the leaf node directly as yes, because there is purity in the classification. There is more information gained in that particular classification. So you need not classify further, right? When the outlook value is overcast, all the training examples are S, means whenever the sky is cloudy, tennis is played irrespective of other attribute values. That is what it means to say here. Okay, there is a pure classification provided by this outlook value overcast. So you need not extend the tree on that particular branch. You can leave it there itself, giving the leaf node as yes. Giving the leaf node. Leaf node means last node. Leaf node as yes. Okay. Now come to the other branch. When the outlook value is rain. How many of the training examples are having outlook value as rain? Total 5 training examples, D4, D5, D6, D10 and D14. Out of them, how many are positive? 3. How many are negative? 2. Again, there is ambiguity, there is uncertainty in the classification. Means the decision tree has to still consider some more attributes in order to make this classification proper, pure enough. Okay, so still there are 3 positive and 2 negative examples. So further attributes have to be considered. Right? Now, see this. For this particular node, information gain is again calculated. How is the information gain calculated? Now, out of the 4 attributes, outlook is already used. So what are the remaining attributes you have? Humidity, temperature, and wind. Now, at this node, you have to calculate the information gain for humidity, temperature, and wind. How is it calculated? Whenever the outlook value is sunny, what is the entropy with humidity? Again, you have to calculate how many of them have normal humidity and how many of them have high humidity. Right? Now you go to the training example set after the class and see, say there are 3 positive examples. Three positive examples and 1 negative example. And here 2 positive examples and no negative examples. What do you understand here? It is able to do some pure classification. Better classification is being obtained by humidity. That is why by seeing the information gain here, 0.970, 0.570 and 0.019, where is the information gain more? With humidity. So that will be taken as the classifying attribute in this branch. Right? Now you go to the other part. Don't consider this part. Why? Because it has reached the leaf node. It has reached the final target label. So you need not consider that particular branch. Now come to the other branch, rain. This branch, rain. There are 3 positive and 2 negative. Now, whenever the outlook value is rain, you have to calculate the information gain for wind and you have to calculate the information gain for temperature. Why you're not using humidity? It is already used here. Why you're not using outlook? It is already used here. So remaining attributes are wind and temperature. Now you have to calculate the information gain for wind and temperature, and if it is found that wind is having highest information gain, that will be taken as the split point here. And whenever the wind is strong, slow, high, something like that, it proceeds so that it will reach the pure classification at the final stage. In this total process, temperature is not used. Why? Because it is not providing us the better information gain. Okay, so this process is continued as I explained you. How long? This process continues for each new leaf node until either of the 2 conditions is met. This is very important. 2 conditions have to be met. One is every attribute has already been included along this path through the tree, means all attributes should be completely used, right? along the path in the tree, means its ancestors should have covered all the attributes, or the training examples associated with this leaf node all have the same target attribute value, means say 4 values are there, all should be positive and no negative label should be there, or all should be negative and no positive label should be there, means it indicates pure classification. That particular attribute is giving a pure classification. Either you can stop there or you can stop when all attributes are used as root nodes, like split points. Okay, that is where the process stops, and that is the final decision tree the ID3 algorithm gives as output and best fit for the training examples given. Okay, so the final decision tree learned by ID3 algorithm is given here. Initially, outlook is taken as the first split point, then humidity is taken as the next split point, where it is reaching the root nodes with better classification, and overcast already provided good classification, so that is not extended further. And when outlook is rain, wind is again chosen as the better classifier over temperature. Why? Because it is giving good information gain. And when wind is strong, tennis is not played. When wind is weak, tennis is played. It has reached better classification at the leaf nodes. That is why the decision tree construction is terminated. Terminated means it has come to an end. And that is the final decision tree. This is the final decision tree that is built by the ID3 algorithm. Now, if I say just concentrate, I am giving you some values, you have to tell me whether tennis is played on the day or not. Outlook is raining, wind is weak, tennis is played or not?
Played, ma'am.
If outlook is sunny and humidity is high, tennis is played or not?
No.
No, ma'am.
This is how whenever all the values are given. But say if outlook is overcast, immediately the training and decision tree will not check for any other attribute, because it is guided that whenever the outlook is overcast, tennis is always played. It doesn't check any more attribute values. It directly says that tennis will be played on that day. Right? So this is the optimal decision tree that is built by ID3 algorithm. Why I am saying optimal? Lots of decision trees can be built by using the training examples. But which is the shortest and crisp decision tree, that only will be considered by the ID3 algorithm. Right? And this is the final decision tree. Did you all understand how we built this decision tree by calculating the entropies and information gain? Now in your example, a new set of training examples will be given and you have to go through the training examples, calculate the entropy and information gain for each attribute and at each and every step of this decision tree and construct this decision tree, right? So you're fine, and you have to show how many of the training examples are at this particular node, how many of the training examples are classified, and finally, what is the purity in the classification at the leaf nodes. All that have to be clearly mentioned. Okay. Now in our next class, I'll give you 15 minutes break. You can take a break and come. In our next class, we'll see what is the hypothesis search space in decision tree algorithm and what is the inductive bias that we assume for this decision tree learning. Any doubts in this calculation? Please let me know so that in your next class, I'll try to cover those doubts. Okay? Take 15 minutes break. By 12:05, we'll start the next class.